Thank you. Go ahead.
Okay. So yeah, thank you everyone. Thanks for having me today. So I'm Marion Pillas, as Christina said. I'm a postdoctoral fellow at University of Liège. And so I'm going to talk about the work I've been doing with a lot of collaborators about Kilonovae associated with neutron star-black hole mergers and taking as example the NSBH candidates that occurred during the fourth gravitational wave observing run. So you have the list here of the collaboration slash telescope that participated in this work. So I will start with an introduction on this kilonovae from neutron star black hole mergers, and then I will discuss the strategy that have been performed in order to observe these NSBH candidates during O4. Then I will show how we can place constraint on the properties of these events, and I will finally conclude about what we learn and what kind of what constraint we were able to put here. So basically, the objective to summarize, the objective of this talk is to discuss the question: why didn't we detect any Kilonovae counterparts of the NSBH candidates during the fourth gravitational wave observing run? Was there because there were no Kilonovae emission from these NSBH candidates, or did we miss it? And in that case, what could be the properties in terms of ejecta and viewing angle of this kilonovae that implies that we missed it. So yeah, you have the archive link of this paper and the QR code if you want to find it quickly here. And so the paper has been submitted to PRD. So for the introduction, so to neutron star mergers, they are really complex objects that involve many fields, and to study them, we have this interdisciplinary ecosystem that connects nuclear physicists in dense matter to the expertise of astrophysicists and theoreticians. But we also have data from both gravitational wave detector, like a Virgo, and also more traditional telescope that looks for the kilonovae counterpart. And so here I am in the middle of the modeling and observational science. And so here is this study and this talk. So for the introduction, just a reminder, this compact binary coalescence system involving at least one neutron star can be qualified as multi-messenger even because they can be observed through numerous signatures that are represented in this figure. And so the only example that we have so far of such a multi-messenger event, it is GW170817, GRB170817A. So on the 17th of August 2017, we observed the first we observed the first detection of a gravitational wave coming from a binary neutron star merger, and you can see the nice chirp, the nice gravitational wave signal that we saw in LIGO Virgo detectors, so in the time frequency plane here. And with this gravitational wave signal, in coincidence with this gravitational wave signal, we saw transient counterparts across the entire electromagnetic spectrum. And so here you have a nice sketch of this electromagnetic aftermath that we saw in the case of 170817. And so the first signal, the first signature that we saw after the merger, around 1.7 seconds after the gravitational wave signal, was the prompt emission of the gamma ray burst. So you can see the light curve of the GRB at the bottom of the slide. And so we also observed the afterglow in radio and X-ray of this GRB 170817A. And of course, around 11 hours after the detection of the gravitational wave, we observed in association to this joint detection a kilonova signal, a kilonova counterpart, which is, as you know, an optical near-infrared counterpart witness to the nucleosynthesis of heavy elements during the merger. So it basically comes from the ejected matter during and after the merger. And so this kilonova is very important because it brings crucial information about first the sky localization of the source by finding the host galaxy, but also it brings crucial information about the environment of the merger. And so you can see on the right the beautiful light curve of the Kilonovae associated with 17OA17, and that for a different filter. So this Kilonovae associated to 17OA17 was the first and only confirmed kilonova seen in association with a gravitational wave. And this was from a binary neutron star merger. But in theory, neutron star-black hole mergers, they can also produce a kilonova signature. But it requires some favorable conditions. So first, a small mass ratio in order to so the neutron star is not directly swallowed by the black hole. But also a high black hole spin. So the neutron star is disrupted by the black hole. And also it depends on the compactness of the neutron star. So basically it depends on the model of equation of states you're considering here. And so numerous models have been emerging over the last years with the aim of modeling the kilonova as accurately as possible. And they usually divide, in the case of the neutron star-black hole merger, they usually divide the kilonova by two types of ejecta. The dynamical ejecta, which is non-spherical, lanthanide-rich component in the optical near-infrared wavelength, and which comes from the tidal disruption of the neutron star. And then you have the disk-wing ejecta, which is spherical in the equatorial plane here. And so this ejecta is a contribution from the post-merger accretion disk. And so these properties of the kilonova, together with the other properties like the geometry of the kilonova, so the viewing angle theta here, or the lanthanide, the half opening angle of the lanthanide-rich component, so the phi. All of these properties, they are imprinted in the kilonova light curve. And so in this work, to study these possible kilonova from neutron star mergers, we have to base ourselves on a model. And so here we have chosen Anand-Boula model, which model the kilonova from neutron star-black hole mergers. And it covers the dynamical ejected masses going from 0.01 to 0.09 solar masses, the wind ejected masses going from 0.01 to 0.09 solar masses. It covers theta going from 0 to 90 degrees, and it sets the half opening angle phi to 30 degrees. And so in this work, we have access to almost 900 light curve covering this parameter space and computed in 21 different filters. And so through this talk, I will define, I will define the word kilonova scenario when talking about one specific configuration of dynamical ejecta, wind ejecta, and theta. So let's go back a little bit to 2004. So the first gravitational wave observing run has started in May 2023. And up to July 2024, there have been 4 NSBH candidates that have been detected. Among them, there is one confirmed event, which is 0529. You have 2 NSBH candidates, 18H and 27C. And one low significance candidate, which is, I will refer to it by 22ED. And so despite a massive follow-up from the optical community, there was not a discovery of a clear kilonova counterpart. However, even a non-detection can help constrain the source properties. And here, I'm talking about the quantity of ejected matter and the viewing angle mostly. So in this work, as I said at the beginning, we first take a critical look at observation strategies from the optical community. And then, given the non-observation of a kilonova, we set constraints on source ejecta and viewing angle properties of the 4 NSBH candidates. So let's start with the first bullet point here. So we assume that in order to maximize the chance of detecting a kilonova, at least one observation should be done at the time of the brightness peak. And this peak time, it depends on the kilonova properties, the ejecta, but also the wavelength of the photon, so basically the filter you're looking at. And so we decided to compare the time of optical observation with the predicted peak time from the simulated kilonova light curve from our model grid, and that for numerous filters. So the results are presented on the following slides. So this one, and this one. And so just to give you an example, so basically here we histogrammed in gray the peak time distribution of our synthetic kilonova population, and that's for numerous filters. And then in color square, we show the time of the observation that have been performed during the follow-up of the 4 NSBH candidate. So each row is one NSBH candidate, and each column represents one filter. And here, I have done that in the paper. It's shown for all the filters that have been used to observe and that we use in the paper. So I have also highlighted to show you the KNC observation in R band and also in C band for 22 ED here. And so to give you some key numbers about these histograms, so there are cases for which the follow-up, the temporal follow-up, have been well performed. It's the case of 18H and 22 ED. So for example, on the left, you can see that in the observation in test band, so made by TESS here, covered the peak time, the peak time of almost all the kilonova, the synthetic kilonova population. For 22 ED, we have the peak time of 82%, for example, of the kilonova population that have been covered in R band. And for 0529 and 27C, there have been less observed due to large sky maps for 0529 and far distance for 27C. And so you can see also, for example, in R band, that the later time strategy is not always realized, while the prompt strategy has been sometimes well demonstrated. And so this might explain that, for example, we missed, for example, the kilonova emission if the one of the scenario falls in a gap here where we don't have any observation. We have not maximized the chance of detecting the kilonova. And so there are important information about this histogram. And one of them is that there is a necessity, to image the first moment of the light curve, because we want to catch the entire light curve and as much as properties that we can. But it is also important to image 1 day post-merger. As you can see, because the median of the peak time distribution is around 1 day for many filters. However, it's not always the case. And for example, for a near-infrared wavelength, so you have the example of J-band here, we advocate a more flexible approach because you can see that finding the peak time is less obvious from this histogram. So, so in some cases, the follow-up the temporal follow-up has been well performed. In other, it's less, for 0529 and 27C, it has been less observed, for example. So it might explain that we missed some signal. But let's go now to the second bullet here. So given the non-observation of a kilonova, we set constraints on the source ejecta and viewing angle properties for the 4 NSBH candidate. And so we'll proceed as follows. We start from GraceDB alerts because we need gravitational wave public information here, because they will help us to estimate a range of consistent ejected masses, both dynamical and wind ejected masses, and therefore select a corresponding set of simulated kilonova light curve in our model grid. And then we'll be able to compare the magnitude of the synthetic light curve to the upper limit from the optical observation. And so here the spirit is that if the expected kilonova is brighter than what has been observed, then the kilonova light curve and the corresponding scenario, ejecta and viewing angle scenario, is incompatible with the observation. So let's start by the beginning. So we need some information that are on GraceDB alert. And in particular, we are interested here in the probability of astrophysical origin, the p-astro. This numbers, this quantity, it basically tells you what's the probability that your gravitational wave candidate come from a BBH, a binary black hole merger, or a neutron star-black hole merger, or a binary neutron star merger. So it looks like that's the top left image here. And so here we are particularly interested in the way PyCBC Live pipeline, which is a pipeline for a compact binary coalescence system in LIGO-Virgo data. So we are particularly interested in the way they compute the probability of astrophysical origin, because they create a deterministic mapping between the source frame chirp mass and its source classification probabilities. So this mapping is shown on the right-hand figure. So basically, you map your M1, M2 space, and you create some categories, BBH-like categories, NSBH-like category, and BNS-like category. These are the two triangles and the rectangle on the plot. And then, assuming the astrophysical origin of your candidate, so meaning rescaling the p-astro to be 1, you draw your line, your chirp mass line. So basically the chirp mass is a combination of the two masses of the binary. And so you draw your constant chirp mass line, and the fraction of the line that fall in one category is the p-astro associated to this category. So I'm giving an example here for 0529 because it's a public event. It has been published by the collaboration, so I can show the chirp mass estimation. And so this is the mapping. And so knowing this process, you can reverse it to estimate the chirp mass from the p-astro estimation in GraceDB. And so you have the p-astro estimation in the table on the left. And so from this, we estimated the chirp mass. And this is an intermediate result because this chirp mass estimation, it will help us to compute a consistent range of ejected masses. And so to do that, we start from this chirp mass estimation, and we compute a consistent range of M1, M2 masses at constant chirp mass. And then we use these formulas, the Foucault formula, so that are on this slide. I won't go into detail here, but these formula, they allow you to compute the dynamical and the wind ejected masses that are related to the mass ratio of the source, the black hole spin also, and the compactness of the neutron star. And so the compactness is basically related to the mass and so the equation of state here. So we computed the dynamical and the wind ejected masses for several value of black hole spins that are in the table at the bottom, and for different equation of states, some allowing the tidal disruption of the neutron star and other involving more rigid neutron star. And so For each of these cases, different black hole spins and equation of state, we create these maps that are on the right of the wind and dynamical ejecta in the M1, M2 space. So here you have an example for one equation of state and a large black hole spin. And so you can see, for example, that the wind ejecta tend to be higher. So on the top plot, it tends to be higher when both the black hole and the neutron star have a small mass, while the dynamical ejecta in this case tend to be higher when the black hole mass is higher. And so we do that for all our cases of black hole spins and equation of state. And at the end, in order to be as agnostic as possible and to make sure that we don't miss any kilonova potential kilonova scenario, we take the broader upper limit between equation of state and spins. And we have our first constraint on the ejecta, but just based on the gravitational wave public information. So for 18H, we select the light curve, the synthetic light curve in our model grid that correspond to a dynamical ejecta, which is below 0.08 solar mass, and a wind ejecta, which is below 0.04 solar masses. For both 0529 and 27C, we selected the light curve that corresponds to a dynamical and the wind ejected masses below 0.01 solar masses. And finally, for 22ED, given the low significance of this event and in order to be as agnostic as possible, we decided to select all the synthetic light curves from the model grid. And so then so we have our first constraint. Then now we include the observation from the optical community. And so to set further constraint, we proceed as follows. Each optical telescope field has a specific field of view, filter, limiting magnitude, and epoch. And we report them on the gravitational wave sky map. So you have two examples here. On the left for 27C and on the right for 22ED. And here I represented the observation between 0 and 1 day, but I have same kind of plot for observation between 1 and 2 days and 2 and 6 days. And so here, the pixels are colored by the limiting magnitude of the field that are on top of them. And so I extract each pixel. So I extracted all the pixels of the sky maps that fall in a field. And in particular, I am interested in their associated distances because it's a 3D sky map. So you have information of right ascension, declination, and distance per pixel. And it can be very different from a pixel to another. So after that, I can compute the apparent magnitude of the synthetic kilonova light curve that I have selected for each NSBH candidate for each pixel, and so at the corresponding distance. And then I can compare the brightness of the simulated kilonova with the upper limit of the fields, of all the fields that contain the pixel, and at the same time as the observation. And so, as I said, if the expected kilonova is brighter than what has been observed, then it is incompatible with the observation. So again, you have two examples here for 27C on the left, 22ED on the right. You can see in the case of 27C that I have selected here just to show an example, one observation, which are the triangle, you know. And so you can see that in the case of 27C, all the light curves are compatible with this observation. While in the case of 22ED on the right, most of the synthetic light curve from the model are incompatible with the selected observation here. So I go through the entire sky map like this, and for each pixel, I compute a scale reflecting the possibility of a kilonova being present in the data. So the scale is well, it's basically this formula on the slide, but to give you something more visible, I represented the opposite of this scale, so 1 minus S here, on the two sky maps for 27C on the left between 0 and 1 day and 22ED on the right between 0 and 1 day. So in other words, here on the sky maps, the pixels are colored by the fraction of kilonova scenario that are ruled out at this specific location. So you can see that for 27C, it is 0 for a very large region, while in the case of 22ED, it reaches 1 for a lot of pixels, in the center. And so to give you some numbers, for example, for 22ED, I have more than 70% of the sky map between 2 and 6 days. Sorry, I have more than 70% of the sky map that rule out more than 70% of the kilonova population. So it indicates that there is likely no kilonova in the observation. And so just a small focus here, again, on KNC observation of 22ED, for example, just to show you that, for example, this observation helped us placing some constraint and ruling out some scenario. So basically, KNC observation helped us to rule out around like 5% of the kilonova population, which is quite nice, because if every telescope rule out 5 different % of the kilonova population, then at the end we have like a lot of constraint. And the configuration, the kilonova scenario that have been ruled out with this observation, for example, its configuration composed of viewing angle, which is below 36 degrees, and configuration with dynamical ejecta above 0.02 solar mass, and wind ejecta, which is above 0.01 solar masses. And so just to show you that it's nice that because in GRAND-MA and in KSA, we have observation that can be deep enough to constrain some ejecta and viewing angle properties. So thanks a lot for that. So going back to the study, at the end, we decided to associate a deterministic probability to each kilonova scenario of being ruled out. And so this deterministic probability is the formula on this slide, but I have represented it also in the histogram at the bottom. So this histogram, it shows the cumulative fraction of incompatible scenario as a function of the coverage of the sky map that rules them out. So to give you an example, between 2 and 6 days, so the black curve, so for 22ED, we have all the kilonova population, all the scenarios that are ruled out by more than 45% of the sky map. And even we have like 99% of the kilonova population that are ruled out by more than 60% of the sky map. So yeah, at the end, we need to put some threshold and say there is likely no kilonova in the observation. So just to give you some overall number about all these NSBH candidates, because I have shown the figure for 2 cases only. So for 18H, it has not been possible to observe a kilonova emitted from a non-axis collision up to a viewing angle of 25 degrees, assuming a minimum confidence of 8% for the presence of the source in this region. For 0529 and 27C, we could not exclude the presence of a kilonova in the observation. And finally, for 22ED, our results seems to point to an absence of kilonova in the observation with and without gravitational wave. And so for these final results about 22ED, it would mean that we have we don't have any ejecta, and in this null ejecta, it is consistent if we reverse the process, and from the constraint on the ejecta, I go back to the Piastro estimation. This null ejecta is consistent with a Piastro which should be below 0.3. And it is inconsistent with the estimation of the Piastro in Grace dB alert, as you can see on the bottom row of the table. So the question is, what could be the reason here? So first, we are kilonova model dependent, so maybe the model is not good for cases like 22ED. Or in addition to the decrease of its significance, because I said it's a low significance candidate, when LIGO Virgo decreased its significance, they also changed the classification. It was no longer mostly NSBH, but rather it was prefer a BNS-like signal. So maybe we should have taken model grid that described the Kilonovae emission from a binary neutron star merger. Or last reason, maybe the candidate is not of astrophysical origin. And this would be consistent with the decrease of its significance that occurred a few months after the alert by LIGO Virgo. So thank you. I'm done, and I will be happy to take questions.
Wonderful talk. Thank you so much. So you guys can post questions in the chat, or you can just go ahead and ask Marion.
Yes, thank you very much, Marion, for your presentation. And so what is your advice for the future? What could be helpful, or of course, to give you some data is, of course, to achieve the highest upper limit magnitude. And this is better also to reach such maximum upper limit magnitude in blue, if I understand well the first part of your presentation. Could you switch on your mic, please, Marion?
Sorry, I was talking, but I had my mic off. So, okay, so what kind of advice? Well, we are currently working with Sarah Antier and other collaborators more about this, observation strategy and how to maximize the chance of detecting something. And ideally, we would like to implement this kind of pipeline that goes from the information from the public alert on the gravitational wave side and try to create this strategy according to this information, and in particular about the peak time, because if we want to to have observation that constrains some scenario, then observed at the predicted peak time would be very great because it's from maximum brightness. So basically, even if your observation are not very deep, you have chance to constrain things. So we are trying to work on this kind of pipeline to implement things and help people in the follow-up. And yeah, I think that trying to manage this temporal follow-up, like the cadence also of the observation, people are trying to work on that. It will be very helpful. Then also, yeah, coordinate with other telescopes to know when and which location of the sky map people are trying to observe. That will be very helpful. So I think that we have to work on our side to try to coordinate the observation and try to predict what is the best time for the observation, because as you saw, it's not always at the very prompt observation. Sometimes it's like 1 day post merger. In the case of BNS, it's more like 0.7 days, and so we need to figure out how to manage everything. And so I saw a question also from Damien in the chat. Do you expect faster evolving rising time and then from rising time and decaying time kilonova for BNS merger? So it actually, so first it's complicated because I expect, yes, this kind of fast evolution, and then it fades kind fastly, but it depends on, well, it depends on model, it depends on scenario, and it depends also on BNS versus NSBH, because we saw, for example, digging a bit into the models, I saw some scenario for the NSBH case when you expect also a kind of rebrightening at some point, like around 2 days. So I think that also the strategy should be optimized according to this kind of features that we can see in the light curve. And so I see another question. Are the parameter estimation values that are published with and shortly after the public consistent with those of the in-depth analysis by LVK sometime afterwards? Or wouldn't one have to add some wiggle space to decide whether to call for observation after an alert? So let me just think again to your question, and then I can answer. So maybe you can give more detail about, or explain again, raise your hand and explain again your question, so I make sure to.
Hans,
I
your
can't.
audio sounds weird.
Okay, but okay, yeah, okay. Damien just gave me the hint to answer your question. So yeah, no, it's it's really different alert from, well, really, it's different alerts versus catalog parameters, in the sense that the parameter estimation that are published in the catalog come from the offline results. So they don't use the same waveform model, for example. There are more tests that have been performed to discriminate signal between noise and stuff like that. So they are kind of more accurate, because when you are working with alerts, you want to be fast. So yeah, it's not exactly the same, but I would say that, well, the information in the alerts, well, should be enough, even if they are not as much as accurate as we would like to, should be enough to call for observation, and in particular this this p-astro, this probability of astrophysical origin. But yeah, I was discussing, for example, with like few days ago with some LIGO Virgo person, and for example they told me that maybe they will try also to push to put the inclinations of the viewing angle in the sky map, so releasing in the alert, because as you saw also here, we are putting some constraint on the viewing angle, and if we have this information in the alert, even if it's not like really well constrained, it will be like very helpful to try to predict the follow-up.
Marion, I think there was a question of David in the chat.
Okay, I didn't see it.
I can read it for you if you want. It's do you work with Gaia catalog if the candidates are in our galaxy?
I will not work with Gaia catalog here. Well, I guess they are not in our galaxy. Well, I'm big. Well, on my side, so I was not really on the observational side of this project. So I'm basically using the data people are giving to me from the all collaboration. So but I didn't work with this catalog.
And David, maybe you can explain, because the candidates you mentioned are the optical transient candidates that people are funding during their follow-up campaign,
Okay.
or is it related to the true, let's say, NSBH candidate, because NSBH candidates are very likely extragalactic
Yeah.
sources, so they are not in the galaxy, but transient candidates can be galactic. So I'm not sure if this was the question actually.
And just to complement here, we only took galaxy targeting and tiling strategy observation for this work, and we didn't include all the list of candidates from these NSBH candidates because the region of the sky was really small, and so when we computed like the coverage and weighted by the sky map probability, it was too small, and so we neglected it.
Yes, and what about O4 campaign for the coming weeks or months? Everything is going on as scheduled?
So right now we are in the commissioning, so there is basically no observation until June, if I remember well. But after that, we will, yeah, there will be observation until like October, I think. And so far, except on February, where we received the fifth NSBH candidate alert, apart from that, there was not any neutron star merger candidates. But so yeah, the plan is to do kind of work like that, also with the fifth one, and maybe it can lead to student project or something like that. So I will probably ask Damien for KNC observation one more time if it's okay for everybody.
And there was one more question from Damien. During the follow-up campaigns, we usually cross-match our optical transient candidate list with catalogs such as Gaia DR3, among others. He just letting you know that.
Yeah, it was not a question, but more a comment to maybe complement
Yeah.
what David wanted to say here. So yes, we indeed use the Gaia catalog, but for cross-matching the transient candidates we found during the optical follow-up campaigns. But this is just to ensure that our transient candidates are really new sources and not catalog variable sources, pardon.
Okay.
And Marion, if you need data, of course, let me know in case Damien's not responding.
Okay, thanks.
Yes, we are all waiting for those NSBH or VNS candidates. So for sure, we will be 100% involved in the follow-up campaign.
Okay, great.
Okay, any more questions? Denise extends his thanks for the interesting talk and says thank you to the rest of the team. Thank you. Have a great day. All right, any other questions, or are we set for the day? All righty, well, thank you so much for coming and talking with us. It's really appreciated. I enjoyed hearing about it.
Thank you for inviting me.
Of course. Have a wonderful day, everybody.
Thank you, Marion. Thank you, Christina. Bye-bye all.
Bye-bye.
Thanks a lot.
Bye for
Bye-bye.
all.